Welcome to MyProjectBazaar.com. Let me discuss about the process, a new PAPR reduction technique in OFDM systems using linear predictive coding. Let me discuss about the abstract of the project. In order to amplify the OFDM signal with large envelope fluctuations, PAs with large linear range are required, which makes it very expensive. If PA has limited linear range, then its operation in nonlinear mode introduces out-of-band radiation and in-band distortion. It is also necessary to have D2A and A to D converters with large dynamic range to convert discrete time OFDM signal to analog signal and vice versa. PAPR is generally used to characterize the envelope fluctuation of the OFDM signal, and it is defined as the ratio of the maximum instantaneous power to its average power. In addition to this, OFDM system requires tight frequency synchronization in comparison to single carrier system, because in OFDM the subcarriers are narrow band. Therefore, it is sensitive to a small frequency offset between the transmitted and the received signal. The frequency offset may arise due to Doppler effect and or due to mismatch between transmitter and receiver local oscillator frequencies. The carrier frequency offset disturbs the orthogonality between the subcarriers, and therefore the signal on any particular subcarrier will not remain independent of the remaining subcarriers. This phenomena is known as intercarrier interference, which is a big challenge for error-free demodulation and detection of OFDM symbols. These excitation and vocal track components are to be separated from the available OFDM signal. To study these components independently for deconvoluting the given OFDM into excitation and vocal tract systems, components methods based on the homomorphic analysis like substral analysis are developed. As the substral analysis does the deconvolution of OFDM into source and system components by traversing through frequency domain, the deconvolution becomes computational intensive process to reduce such type of computational complexity and finding the source and system components from time domain itself. The linear prediction analysis is developed. Let me discuss about the flow diagram for our process. Initially, generate the OFDM symbols using a large number of parallel narrowband subcarriers instead of a single wideband carrier to transport information. OFDM is a frequency division multiplexing scheme used as a digital multi-carrier modulation method and is essentially identical to coded OFDM and a discrete multi-tone modulation. It is used in such diverse applications as digital television and radio broadcasting, wireless networking and broadband internet access. OFDM has also been adopted in some military communication system. In an OFDM scheme, a large number of orthogonal overlapping narrow band and subcarrier transmitted in parallel divide the available transmission bandwidth. The separation of subcarrier is theoretically minimal, such that there is a very compact spectral utilization. The attraction of OFDM is mainly due to how the system handles the multipath interference at the receiver. And linear predictive coding. The implementation of linear predictive coding is a method for signal source modeling in OFDM signal processing. It is often used by linguistics as a format extraction tool. It has wide application in other areas. LPC analysis is usually most appropriate for modeling vowels which are periodic, except usually vowels. LPC is based on the source filter model of OFDM symbols. LPC analyzes the OFDM signal by estimating the formats, removing their effects from the OFDM signal, and estimating the intensity and frequency of the remaining bus. The process of removing the formats is called the inverse filtering, and remaining signal after the subtraction of the filter model signal is called the residue. Next, autocorrelation and PAPR reduction has been proposed. Orthogonal frequency division multiplexing is considered to be a promising technique against a multipath fading channel for wireless communication. However, OFDM faces the peak to average ratio problem, that is major drawback of multi-carrier transmission system, which leads to power efficiency in RF sections of the transmitter. The key challenges are ISA due to multipath use, guard interval, large peak to average ratio due to non-linearities of amplifier, phase noise problems of oscillator, need frequency offset correlation in the receiver. Finally, the design LPC OFDM transmitter and receiver. So resultant the signals are analyzed using the peak to average power ratio. The peak to average power ratio is a peak amplitude squared divided by the RMS value squared. It is the square of the crest factor. When they expressed in decibels, crest factor and PAPR are equivalent due to the way decibels are calculated for power ratio versus amplitude ratios. Let me discuss about the running procedure for our process. Select the main.m file in the current folder, write this file and run for executing this process. Here we can estimate the peak average power ratio detection by using linear predictive coding. Here we obtain the performance graph for our process. This is the CCDF, that is cumulative distribution function graph for our input signals. This is our BR response, this bit error rate response by varying the SNR values. This is the power spectral density, PSD, for our reducing the power by varying the frequency of the channel. And this is the power spectral density by varying the quadrature amplitude modulation step size. It is m is equal to 16 and m is equal to 32. This is the normalized ACF response for our LPC coded result. This is our probability of PAPR when using the LPC OFDM. This is the probability of PAPR when m equal to 4 to 32 step size, and this is the probability of PAPR when the m step size m is equal to 64 to 2048. This is the BR response when m equal to 4 to 20, where m used in the quadrature amplitude modulation. Here by varying the m step size we can obtain the BR bit error rate. Here varying the QA modulation m step size we can obtain the bit error rate graph. By varying the m step size, here also we estimate the BR performance. Here finally the BR performance obtained by varying m from 4 to 32. Finally we can reduce the power, this peak to power average power ratio using LPC coding.